Welcome back to Codex. Today's speaker is David Rosen from Northeastern. Professor Rosen is an expert in the mathematical and algorithmic foundations of trustworthy autonomy. Today, he'll tell us about certifiably correct machine perception. Take it away, David.
Okay, excellent. Well, yeah, thanks very much for the invitation. It's a pleasure to be here, speaking a little bit about some of our recent work on what we've been calling certifiably correct machine perception. So a little bit of background and kind of motivation for what we're going to be talking about today. My group does a lot of work in robotics, and robotics is the science of physically embodied autonomous agents. And so if you think about, the kinds of functionalities or capabilities that you would like physically embodied autonomous agents to have, all the core capabilities like planning, navigation, manipulation, and so on, all require accurate models of the environment. And so a natural question then is, where are these models supposed to come from? And just to give you sort of a concrete sense of, what is really involved in this, or what I mean exactly by the kinds of problems we're considering about, let's take the example of like an autonomous car sort of driving down the road, right? So if you look at like an autonomous car's eye view of the world, this is the kind of model that it's building internally as it's, driving, right? So you see it's got to do things like keep track of what lane it's in, keep track of where other things are on the road around it, other vehicles, pedestrians, cyclists, and so on. It's got to be able to detect and recognize, things like stop signs, road signage, and so on, right? And so the main thing I just want to convey with this is just that there's a lot of stuff going on, like under the hood, right? There's just like a lot of moving pieces, a lot of moving parts, a lot of things that need to be estimated as this vehicle is trying to just go about its business. And, all of these things have got to be done properly, right? You could imagine, for example, that if you misestimate where, one of these cyclists is, that's going to be super, super bad, right? So, we want to be able to estimate, we want to be able to solve these estimation problems in a reliable fashion. Okay, so I've used this, perception estimation problem or, terminology. What do I really mean by that? When I say perception, really what I mean is any sort of black box that ingests raw sensory data and outputs some model of the world that we're going to use for downstream decision making. And so, there's many different ways of thinking, formulating problems of this type. But if you were to open up, the vast majority of papers that would be in the robotics literature, the computer vision literature, or machine learning, what you were going to see, generally speaking, is a formulation that looks like this, right? So the basic idea is we've got some raw measurements or raw data that came off of our actual robot sensors. We've got some set of model parameters that we're trying to estimate. So, that parameterizes the model of the world we want to use. And so these would include things like, the position of pedestrians, position of the robot, positions of landmarks in the environment that we might want to track or put into a map. And we've got some kind of a loss function that would measure the discrepancy between any particular hypothetical model of the world that I might consider and the actual data that came off of our sensors. That is, what this is really quantifying is how well does a particular hypothetical model explain the data that we actually got. And so just to make this concrete, for those of you who've studied, maximum likelihood estimation or M estimation, that falls into this framework. Similarly, for those of you who do, regularized empirical risk minimization or neural network training in machine learning formulation, that would also fall into a formalism that looks like this as well. So this is quite broad based, and this is the typical thing that you would see in a lot of the engineering literature. And so that's fine. This is a nice, simple, elegant mathematical formulation. In the context of maximum likelihood estimation, you can prove a lot of nice statistical properties that estimation methods that are constructed in this way provide. One thing that's a little bit less satisfying about this formulation, though, is that if in these papers, this is about what you would see, right? Just solve this problem and you will get the answer, right? What they tend to talk a little bit less about is how are you actually supposed to do that, right? And just to make this a little bit more concrete, I claim that actually there's a lot of complexity that is hidden in this seemingly innocuous looking statement. And, in fact, these problems are oftentimes significantly harder than they might at first appear. Why is that? Well, the main challenge here is that, most of the problems that we're interested in solving in applications tend to be both high dimensional, just because there's a lot of states that you want to estimate. And they also tend to be non-convex, oftentimes, and in particular in the case of embodied intelligence, because the parameter spaces over which we are trying to do the estimation are themselves non-convex sets. So, for example, anything involving the estimation of orientations falls into this class. And so, as you guys are probably aware, anytime you see problems that are both high dimensional and non-convex, there should be kind of alarm bells that are going off in your head in the background, because those problems very frequently turn out to be computationally hard in the sense of computational complexity theory, meaning, NP hard or harder. Operationally, the way that this computational hardness often manifests is in the form of a ton of bad local minima that these optimization problems have. So they have an unfavorable optimization landscape. And just to make that a little bit more concrete, what I'm showing you here is an example of what would be considered a relatively simple robotic state estimation and mapping problem. So in this scenario, this car is started in this parking lot. It's going to drive around this parking garage and sort of explore the interior of it. And the objective of this estimation task is to estimate the trajectory that this robot has gone through while it's been doing this navigation. So I claim that for this particular problem, and just take my word for it momentarily, I'll explain how I arrived at this later. What I'm showing you here is the actual true or optimal estimate for the trajectory of this robot. So this is the actual thing that you would want to estimate. And you can kind of see in this trajectory, you can pick out the structure of these internal ramps in this parking garage here in this correct estimate. If you try to solve these parameter estimation problems using some of the traditional sort of first things that you would try, right? Let's just try gradient descent, right? What are the kinds of things that you might get if you find a local versus a global minimum? What you get are things that look like this, right? And so I would just invite you to imagine trying to drive your autonomous car out of this parking garage or find a parking space or something like that, right? Or imagine driving your autonomous car down the Autobahn, like, 120 miles an hour, when this is the kind of, estimate that your estimation methods might potentially return to you, right? So, when I think about, one of the things that keeps me up at night is really questions about this, questions like this about safety and reliability, right? And so a lot of the stuff that my group has been thinking about recently, or a lot of the work that we have been considering over the last several years, has really been motivated by this question of, is it possible to develop estimation techniques that are, on the one hand, computationally tractable, because we need to be able to run these in hard real time on resource-limited mobile robotic platforms, but that also allow you to say, provide some kind of performance guarantees on the quality of the solutions that these estimation techniques are going to return, so that you can say something about safety and reliability of these systems, that we want to deploy in safety critical applications. So that's a lot of what has been motivating a lot of our work over the past few years. Okay, so the main idea that I want to convey to you in this talk, sort of motivated by those applications, is that convex relaxation provides a super powerful approach for building fast and globally optimal optimization techniques that enable you to solve a lot of these challenging estimation problems in practice. And so in particular, some of the stuff I'm going to talk about today demonstrates that you can actually apply this approach to enable the recovery of provably globally optimal solutions under realistic operational conditions. And not only that, but if you're sufficiently clever about how you set up your optimization techniques, you can actually do this in a way that preserves the speed of existing state-of-the-art heuristic local search-based techniques. And so you really get the best of both worlds. You get fast performance, that existing heuristic methods enjoy, but you also get verifiable global optimality, which is important for safety and reliability. And so if you build your techniques in this way, really what you get is this approach gives you then a principled and practical approach to performing robust machine perception in practice. Okay, so what I'm going to talk about then for sort of the rest of this talk is I'm going to use robotic mapping and a specific formulation of robotic mapping called post-graph optimization as a concrete example to sort of illustrate what this approach looks like on a tangible problem. So I'm going to give you guys a very quick sort of lightning introduction to what this estimation problem looks like for those of you who maybe have not seen it before. And then I'll describe both how you can construct effective convex relaxations for this problem, and then how you can actually design practically effective structure exploiting optimization techniques that enable you to solve these resulting convex relaxations very fast in practice. And we'll conclude with some discussion generalizations of this particular technique at the end. Okay, so let's just dive right in then. So for those of you who have not seen sort of robotic mapping before, I'm going to give you a quick sort of cartoon introduction to this. So let's consider that we've got some robot that we want to release into some building, and we want this robot to drive around and construct some map that we might use for navigation or control tasks later on. Okay, so what does this problem actually look like? So, we're going to release this robot. This robot is going to drive around through some sequence of positions and orientations as it's doing data collection. But at each moment in time, this robot can only see a relatively small section of the environment because, sensors have limited range. You can't see through walls and things of that sort. And so if you look at the actual raw data that comes off the sensors of this robot, it kind of just looks like a jumbled pile of, little cross sections, little pieces or cross sections of small portions of the environment. And so this is what the actual sort of raw data that you have looks like. Now, if you knew what the actual sequence of robot poses that your vehicle had traversed as it was doing this data collection was, you could imagine taking each one of these little scans here and sort of attaching it to the pose of the robot from which that scan was sampled. And if you were to do that, effectively what would happen is you would sort of unfold or co-register all of these individual scans into a common coordinate system that would produce for you a coherent, properly registered model of this building that you would explore. And so this is what we want, right? This is what we would like to achieve. The problem, of course, is that there actually isn't any sensor that will directly tell you what the sequence of poses your robot traversed was. Like, GPS doesn't work indoors, doesn't work underwater, doesn't work in space, or at least in, extra planetary, non-Earth planetary bodies. And so there isn't anything external that will just directly tell you where you are, right? We have to actually estimate this ourselves. And so then the question becomes, okay, well, how are we going to do that, right? So the main insight that we typically exploit in order to address this problem is the following. Suppose that I look in the environment and I see some landmark, like a lamppost or a chair or something like that, and I can pick out that landmark across multiple scans that my robot has taken. As my robot moves through the environment, where that landmark shows up in either laser scans or images that my robot might collect, that landmark is going to show up in different places in those individual scans, those individual images or those individual laser scans. And the idea is that because that apparent motion of that landmark in those scans is actually caused by the motion of the vehicle itself, anytime I can identify a common landmark in more than one scan, if I look at the apparent motion of that landmark, what that is actually telling me is it is telling me at least partial information about how the robot moved between when those two scans were collected. And so if I go through my scans, my collection of images that I've taken, and I pull out, or I can identify when I'm looking at the same object in different scans, I can exploit that information to build up a network of estimated relative motions that relate the unknown poses at which the robot collected those individual scans. Okay, so there's a question on that now would be the appropriate time to ask, because this is sort of the model that we're gonna use hereafter. But the basic idea is that mathematically, abstractly, then what this allows us to do is it allows us to build up as this robot is moving around, as it's sort of driving around this environment. If we look for these common landmarks across multiple scans, what that allows us to do is it allows us to build up an estimated set of, or a network of estimated noisy spatial relations between the robot poses that we're trying to estimate. So, yeah.
So are these landmarks selected by a human, or are these like automated?
Right, yeah. So this is an automated process, and there are sort of standard techniques for doing this. For if you do like visual mapping, for example, there are standard techniques that you can use to pull out visually distinctive features in the environment from an image. And then, attached to those visual interest points, what are called feature descriptors, right? And so these would be feature vectors that notionally tell you something about what the visual appearance of that image is in a small local neighborhood around that point. And so the idea then is if you can pull out these distinctive features that are strongly localizable, and you would expect to show up across multiple scans or images, and if you can tag them with descriptors that somehow provide the ability to discriminate different points, or somehow are, how do I put this? They capture information about the local appearance of the scene. And so what that allows you to do is if you can tag these feature points with these local descriptors, by comparing descriptors across different images, you can try to determine when you might be looking at the same point, is the idea.
And hopefully the scene isn't changing Well, you're flying through that.
Hopefully the scene is not changing. Yeah, I mean, that is definitely a problem. Like practical implementations of SLAM systems will contain in them, mechanisms for proposing potential feature correspondences across scans, and then doing some kind of geometric verification or outlier rejection on those putative candidate matches to check whether or not the things that you are potentially considering as associations are geometrically plausible. So that's a whole separate can of worms. I'm not going to talk about that in this particular talk, although it is an important issue. Yeah, but the punchline is, there are sort of automated standard techniques that one can use to try to find these corresponding features across these scans. Yeah. Okay, so the output of this, though, is that as this robot is driving around, you're building up this estimated network of spatial relations between these unknown poses. And so you can sort of represent this problem as a graph in which these estimated relative motions are associated to the edges, and the unknown poses are the vertices in this graph. And so this is essentially, this graphical model then essentially gets us to a formulation of robotic mapping called pose graph SLAM. And so the idea here basically is, we have this collection of unknown poses, we have this collection of estimated relative motions between them, and what we want to find then is a joint estimate of these unknown poses that somehow maximally, is the best explanation for these estimated relative motions, these pairwise estimated relative motions. And so under some, reasonable noise model, I claim that you can formulate this as a maximum likelihood estimation problem that looks like the following. And so the main thing I just want to point out here is, the details of this are not super important. The main thing I just want to point out here is that the objective here is a nice convex, sum of square, linear sum of squares, super nice convex objective. Why is this problem hard? The problem is hard because it is high dimensional. Again, if you can imagine, if you're trying to map a large building, you might need, several thousand scans in order to completely cover that building footprint. So that's a relatively high dimensional problem. And it's non-convex because we're doing parameter estimation over poses. That is, robot positions and orientations. Orientations are a non-convex set. Therefore, this is a high dimensional non-convex problem. And in fact, this particular PGO formulation is known to be NP hard. So that's not great. That's not great if you want to solve large scale instances of this, right? So that's maybe point number one. Point number two is, we came to this problem through looking at robotic mapping. But it turns out, and perhaps it's not surprising from this description, that PGO is a ubiquitous fundamental problem in geometric estimation. So it shows up in robotic mapping. It also shows up in 3D in 3D visual reconstruction and in multi-sensor rig calibration. So if you want to calibrate sensors on a robot, it's also closely related to problems like max cut, which can be viewed as really a specialization of this. And there are very closely related problems that even show up in structural biology or molecular biology involving things like cryo-electron microscopy. And so basically any problem in which you're trying to rigidly align data that was little pieces of data that were collected by taking local measurements with a sensor, you would expect a problem like this to show up, any sort of data co-registration problem in 3D space. So this problem is hard, but it also is one that if you could make forward progress on it, would have ramifications for a bunch of. Okay, so how are we actually going to solve this then? So the main idea that I just want to convey here is, because this problem is NP hard, you should not expect that we're going to be able to solve, machine perception problems like this in general, unless you think P equals NP and quantum computers are going to solve all our problems for us and so on. I personally don't, but maybe that's a matter of taste. However, if you stop and think about the sentence for a second, what you might realize is that this word in general is doing a lot of work in this sentence, right? All this means, like, NP hardness is a worst case computational complexity result. So all that means is that if you give me some problem class and some algorithm that you claim will solve every instance of that problem in that class, I can go in and I can pluck out, a small one or a handful of problem cases that are going to have to make your algorithm work super, super hard, something, akin to exhaustive search in an exponentially large space. But that worst case complexity analysis doesn't say anything about how prevalent those super adversarial hard cases are. And so what you might hope is that the picture looks something like the following, right? That maybe there's some kind of a separation between the super hardcore cases that make this overall problem class hard and the kind of cases that you might expect to actually show up in like real life engineering applications that maybe are somehow a little bit simpler to solve, right? That is to say, maybe it's possible to somehow well approximate not the whole set of problems, but a subset of reasonable instances that are the ones we actually care about, right? And so it turns out, number one, I claim this picture is actually correct. But number two, even if it is correct, the key question then is, okay, that's nice notionally, but how are you going to actually produce these reasonable approximations? And so the main tool that we want to propose in this talk for doing so is convex relaxation. So that is, we're going to construct a convex approximation to our original problem and use that to search for high quality approximate solutions efficiently. And so this is nice because there are fairly standard machinery for constructing these approximations. So things like convex outer approximation, Lagrangian duality theory, Lazaire or moment or SOS relaxations of polynomial optimization problems are all sort of standard classes of mathematical machines that will algorithmically generate convex approximations for broad classes of problems, like polynomial optimization problems, for instance. So it's fairly easy to mechanically construct these. And then number two, because convex problems are nice and doing convex analysis is a lot easier than non-convex analysis, oftentimes when you replace your original problem with a convex surrogate, because those problems are easier to analyze, it is often possible to actually prove formal performance guarantees on the quality of the estimates that you extract from these convex approximations. And I'll show you an example of that a little bit later. Okay, so this is the overall strategy that we are going to adopt for trying to solve these problems then. Okay, so what I'm going to show you then is how we can sort of take this idea and apply it concretely to this PGO SLAM problem that we're considering. And I'm just going to, before we do that, I'm going to show you one quick simplification we can apply to this problem that is sort of independently interesting or kind of a useful trick sometimes. Okay, so if we look at our original SLAM objective, what we might notice is that if I consider just performing partial minimization over just the position estimates, if I consider just the position estimates, this problem is just a totally standard, linearly squares problem. And so it is possible to solve for optimal assignments to these position estimates via matrix factorization. In particular, we can use a generalized Schur complement. And it turns out that the optimal assignments to these positions can be written by means of this generalized Schur complement as linear functions of our rotations. So if I fix a set of rotations, I can immediately determine the corresponding optimal set of translations, and that relation is linear in the R's. And so if I think about that for a second, what that means is that I can take this optimal assignment to the translations as a function of the rotations, and I can just plug it immediately back into my original objective. And what that effectively does is it analytically eliminates these translation or position variables from this problem, and thereby reduces this problem to an equivalent but simpler estimation problem that now only involves these rotational variables. So that's just using partial separability. It's a pretty straightforward algebraic simplification, but it just means that it allows us to now contemplate this more concise, like a little bit simpler problem that has kind of like a more a nice compact matricized structure. Okay, so now I'm going to show you where the real magic happens. So this is the actual, this one slide is like the, where is really the secret sauce for our technique here. Okay, so let's take a look at this SLAM formulation here. What I might notice if I look at this is that the specific manner in which my decision variables enter this problem is only through this symmetric outer product R transpose R. Okay. So let's take a look at what variables of that type actually look like. Well, so first off, this is going to be a symmetric and positive semi-definite matrix because it's a symmetric outer product, so that's pretty clear. And because this decision variable R is a row matrix of rotations, and R transpose R is the identity for any rotation, it's pretty easy to see that this PSD matrix is going to have a block diagonal that is comprised of identity matrices. Okay, so every feasible point for my original problem is going to look like this. Why is this interesting? This is interesting because if I look at what the right-hand side of this looks like, well, the set of PSD matrices is a convex cone. And the collection of all matrices that have this prescribed block diagonal is just a linear subspace. And so all of my original feasible points are contained in this set C, that is the intersection of the PSD cone with a linear subspace. And so this is advantageous because these are well-studied objects. Intersections of the PSD cone with linear subspaces are well-studied objects called spectrohedra. and those are well-known convex sets. And so what this insight allows me to do is simply to say that if I simply consider replacing every instance of R transpose R with a generic PSD matrix that has this prescribed block diagonal structure, then what I obtain is a convex relaxation of my original problem in the form of a semi-definite program that is obtained by expanding the feasible set for my original problem. So the objectives of these two problems are the same, but the feasible set is larger. And so therefore I have a nice convex relaxation. Okay, so now we can sort of put these two problems side by side. And so we might say, okay, that's great, Dave, but like, why is this convex relaxation interesting or useful? Well, two things. First off, it's pretty easy to see that this optimal value is going to be a lower bound on the optimal value of my original problem because I'm minimizing the same objective over a larger set, and so I can always do at least as well. So that's relatively straightforward. That's observation one. Second observation, which is more interesting, is if I were to solve this convex relaxation, and if the minimizer that I were to obtain happens to admit a factorization that looks like this, right? So Z happens to be a low-rank solution, and that low-rank solution happens to admit a low-rank factorization in which the individual factors were like some row matrix of rotation matrices. It's easy to see that those row matrices would necessarily be an optimal solution to my original MLE. And that's because it is a feasible point, and that feasible point would attain an objective value that coincides with this lower bound, and therefore must be globally optimal. And so you can say, okay, that's great. That sounds super cool. Unclear why I would ever expect this to happen because I constructed this by adding a bunch of points in there that don't correspond to anything like that, right? The main reason that we are interested in this particular class of relaxations is that we've actually proven that this favorable circumstance does actually generically hold, provided that the noise on your data is not too large. So this is sort of the main result that we prove in our original paper on this. There's a bit of text here, but so let me just walk you through what the statement is really saying. For any problem that you give me, there is going to be some unknown ground truth configuration. Right, there is some true sequence of poses and so on that this robot went through, although I don't know what it is. And so in principle, there are some noiseless idealized measurements that in this case would be the true relative motions between those robot poses that my robot traversed. So what this theorem says is that for a given ground truth configuration of a problem that we're interested in solving, there is some bound on the admissible noise for your actual data, your actual noisy measurements, such that as long as the noise in your data is not too large, as long as your actual measurements don't exceed this noise threshold, then this semi-definite relaxation is going to have a unique solution, and that unique solution is exactly going to is going to factor in exactly the way that we require in order to recover from it a global minimizer to our, in general, intractable, super high dimensional non-convex SLAM estimation problem. And so what this theorem is really saying then is that not in all cases, but under reasonable cases, that is, cases in which the noise on the data is not excessively large, we can actually recover a global minimizer, a verifiably global minimizer to our hard mapping task simply by solving this convex semi-definite relaxation. And so this gives us a direct global optimization technique that we can use to efficiently solve this generally intractable class of hard estimation problems. Not in all cases, but in an operationally reasonable or operationally relevant restricted setting of limited noise. So that's the main idea behind our approach. Is there any questions on this so far? This is sort of the main algorithmic approach we're going to use. Going once, going twice. Okay, everybody's on board.
Is there a
yeah?
Do you have a sense of how beta varies with Q bar? Like,
yeah, that's a good question. That's a good question. Yeah, we don't have. I'll show some empirical results on this in a little bit. We don't have sharp quantitative statements on this yet. In part because what that entails is hypothesizing some particular noise model and then trying to propagate or consider how that noise model transforms as it's being propagated through both nonlinear maps in your measurement functions, and also actually in some sense what you really want to consider is propagating that through the process of function minimization when you're computing this maximum likelihood estimate, right? As you can imagine, controlling that propagation gets a little hairy, and so there are bounds that people have been able to derive on what beta can be. Those bounds are empirically pretty loose. They're pretty loose, just because the analysis gets very tricky. What I can tell you is that, and what I'll show a little bit later, is that operationally, any sort of reasonable implementation of a robotic mapping setup, it has noise that is well under this critical threshold empirically. So, yeah. Okay, so now that we've got our nice SDP set up, then the question becomes, okay, well, now all we have to do is just solve this, right? So, let's just try using our favorite off-the-shelf interior point method to do this. So what I'm going to show you here is what trying to directly solve this resulting SDP relaxation looks like using a standard interior point method applied to what would be considered some relatively small scale lightweight examples. So this is a simulated cube data set. What I'm showing you here is the size of this data set, that is, the number of vertices per side in this cube, followed by how much time is required to solve this resulting SDP relaxation. And as you can see, what this is showing basically is that, we've got a test case with a couple of hundred poses in it. And this is requiring, several thousand seconds to solve, right? So order of tens of minutes, right? In order for this technique to be competitive with existing heuristic methods, I would be needing to solve, problems that are roughly 2 orders of magnitude larger than this. And I would be needing to solve those problems on the order of seconds or less, right? And so this scaling is not great, right? This would be considered, completely intractable for trying to use this estimation procedure as a basis for real-time control of like interactive robotic systems, right? I can't sit around waiting 1,000 seconds to try to figure out where I am in space, right? That's not reasonable, right? And so maybe this looks maybe not quite so great, right? And in fact, if you think about why is this so slow, I mean, well, it's because we have these giant matrix decision variables, right? I mean, if our matrices have dimension, if our mapping problem has n variables in it, the decision variables that appear in our relaxation are matrices of dimension, n squared, right? They're n by n matrices, right? So the actual decision variables are of size n squared, which means the Newton system has size n to the fourth, which means, solving this Newton system using, the sort of basic direct factorization techniques you would think of is going to, cost n to the sixth, right? And so, although SDPs are polynomial time solvable, what this indicates is that like interior point methods for SDPs, although polynomial time, have an exponent that's like n to the sixth, right? And that is not great when you consider that this is already slow and we need to solve problems that are 100 times larger than this, right? Every time I go up by a factor of 10 in terms of size, I make my problem 1,000,000 times harder to solve in this way. And we need to get 2 orders of magnitude out of a system that is already intractably slow, right? So that's not great. Like that's not great from a practical standpoint. And so, what are we going to do? Well, what this suggests is that we're not going to be able to use standard techniques to solve problems of this type, but maybe we can try to be a little bit more clever and build some specialized techniques that will help us to solve these problems faster. Okay, so how are we going to do that? We're going to exploit the fact that we know that so in the previous theorem, we proved that when this relaxation is exact, it has a unique solution, and that unique solution is going to be low rank. It's going to be a rank D, where D is the dimension of your original problem. And so what we are going to do is we are going to exploit the fact that we know that these problems should admit low rank solutions to devise specialized SDP optimization techniques. And the way that we're going to do that is by exploiting a neat technique called Beer-Montero factorization. So the idea behind this is just that because we expect our original problem to have a low rank solution, we can exploit this by simply replacing the decision variable in our original SDP with an assumed rank restricted factorization of this type. And so if we do that, number one, we're now performing estimation over a much lower dimensional variable, right? This variable is of size r by dn as opposed to dn squared. And so if r is less than d, or if r is less than n, and which is usually much, much smaller, like several orders of magnitude smaller, this optimization problem now has a dramatically reduced dimensional search space. So we can search through it much faster. Secondly, again, because outer products of this sort are PSD and symmetric by construction, this PSD constraint, our original problem, now becomes redundant. And so this rank-restricted approximation takes the form of a standard nonlinear program that we can just solve using, off-the-shelf nonlinear programming methods rather than more complex STP optimization techniques. And then finally, we can even do one more further simplification, which is just that if we look at this constraint system, if you consider that this outer product matrix Y transpose Y and look at the constraint that its block diagonal has to have identities on it, that's equivalent to the statement that yi transpose yi, where yi is the ith block of this block matrix Y. That has to be the identity. And for those of you who have studied maybe some differential topology before, you might recognize that the set of things that satisfy this system of constraints is actually a smooth manifold called the Stiefel manifold. And so, what this means is that if I think of Y as being sort of a row matrix, each of those individual elements in that row matrix is going to be an element of a Stiefel manifold. And so this rank-restricted Vieira-Monteiro factored form of this semi-definite program turns out to be just can be thought of as an unconstrained Riemannian optimization problem. So it looks just like unconstrained optimization is the punchline. Okay, so the idea then is we're going to try to solve these low-dimensional, rank-restricted Riemannian optimization problems in order to search for low-rank factors of a solution to our original STP is the idea.
Hey, David, just so I have a sense of scale, I think in your use case, D might be 3, and then
Right.
would R be like 6 or 10 or
yeah, R is going to be.
That's
right. Yeah, so that's a good point. So you get to pick R. You get to pick R. And so, in fact, there's not one, but there's really a hierarchy of these that you get depending upon how you want to pick this this maximum rank parameter. But the idea, the utility of this is that so we know from our previous theorem that in the event that this relaxation is exact, the rank of our solution is going to be exactly D, right? So we know that that we have to make R at least as big as D, but the hope is that we'll be able to get away with making it not much bigger than D, right? And while still finding a solution to our original problem. But yeah, so roughly speaking, you would want to pick like D plus 2, D plus 3 would typically suffices. Yeah. Okay, so for those of you who've been sort of following along so far, you might be thinking to yourself, okay, well, wait a minute, something weird has just happened, right? Because we started with this hard quadratic optimization problem, and we're like, okay, well, that's NP hard, that's super hard, don't know how to solve that, right? So let's maybe take that and relax it to an STP, which is great because it's convex, right? But then we're like, okay, well, that STP is now also very hard to solve just computationally, like practically. And so we're going to try to do this low rank factorization search by, again, sort of replacing Z with yet another low rank factorization. And so if I compare these two problems, it's like, okay, well, I took a quadratically constrained quadratic program, relaxed it to an STP, and then used Vieira-Monteiro factorization to produce another quadratically constrained quadratic program. So like, what is the actual benefit of doing this, right? So it turns out that there is actually a benefit to doing this, although it's a little bit subtle. And the benefit to doing this is that when I'm solving this problem, I am looking for a solution to an STP. And because the STP is convex, stationarity conditions are both necessary and also sufficient for global optimality. And so basically what that means is that even though I'm doing local optimization here, if I happen to find a low rank factor that corresponds to a solution to my STP, I can actually recognize it when I'm looking at it. And not only that, but it turns out that so the idea would be, let me apply fast low dimensional Riemannian optimization to this rank restricted Riemannian STP. I'm going to get a low rank factor. I can then check whether or not that low rank factor satisfies the KKT conditions for my STP. And that's a pretty straightforward result to check that. The more interesting thing happens when it in the event that my low rank factor Y is not. Well, let me say this instead. I'll cut to the chase. The result basically is, or one of the results that have been proven by Bumal, Vorninsky, and Bandera is that if I solve this rank restricted NLP, and the resulting solution that I get is a second order critical point, and also rank deficient, that it is guaranteed to be a global minimizer of both this problem, and also that that low rank factor actually is a low rank factor for a solution of the SDP. And so it's easy to produce a second order critical point by just applying a second order local optimization technique to this rank restricted nonlinear program. And so the only hard part of this is just trying to find a point that is rank deficient. But if you stop and think about that for a second, this fact then sort of suggests a very natural algorithm, which is just, I just solve a sequence of these problems. I apply local optimization to a sequence of these problems. I can find second order critical points by doing that. And then I simply check rank deficiency. And if my point is rank deficient, then I know I'm done. Otherwise, I can just augment the rank by 1 and just try again, starting from that, the stationary point that I found in the previous solution. And so if you do that, yeah, so we can use local optimization. So that's a way of sort of sequentially applying local optimization, fast local Riemannian optimization to search for global solutions to this SDP. And so if you sort of, so if you sort of follow that algorithm that I just described a moment ago, you get something, that algorithm is something called the Riemannian staircase. And it's actually is quite simple. So you start at some initial rank parameter R0 with some initial point. And then all you do is just apply your favorite fast second order local optimization method to this Riemannian low rank optimization problem. That gives you some second order critical point. You then simply check whether or not that point is rank deficient. And if it is, then that theorem shows that you're done. You have a globally optimal solution. If it's not rank deficient, you just increase the rank by 1 and then just try again, run second order optimization again, starting at this point. And so this algorithm is super simple, but it's also super fast. And the main reason that it's super fast is that effectively all you are doing is just wrapping a fast, second order Riemannian optimization method inside a slight, meta algorithm that is just doing rank checking and then rank augmentation, right? So 85, 95% of the computational effort is simply calling these fast second order low rank optimization techniques that look almost identical to the heuristic low rank optimization, low rank or low dimensional search that you would be applying just to apply local optimization to your original estimation problem. And so this is really kind of the thing that to my mind makes this algorithm kind of neat, is that by augmenting these rank parameters, you're just giving yourself just a few extra degrees of freedom, just like 1 or 2 extra dimensions of degrees of freedom in the parameters that you're estimating. But that little bit of extra maneuvering room turns out to be enough in many cases to escape local minima and to allow you to descend to recover provably globally optimal solutions for these problems. And it does so fast because you're using the same sorts of fast optimization techniques that you would be using to just do pure local search on your original problem to begin with. Yeah. Okay, so if we combine all these things together, then we get an algorithm called SE-sync that looks like the following. What we're going to do is we're going to apply fast low dimensional optimization to find a second order low rank factor, or to find a low rank solution or low rank factor of our SDP solution. Once we have that low rank factor, we can immediately compute the optimal value of this SDP, which gives us a lower bound on the value of our original maximum likelihood estimation. Because we have recovered this high dimensional factor, we need to extract from that rotation estimates, like valid rotation estimates, in our original D by D matrix space. We can do that just by using an SDP. Projection onto the set of orthogonal or set of rotations can be done just by computing an SVD. That's a well-known closed form thing. And then so finally, what that will give us is it will give us an estimate for optimal rotational states for our original problem, original mapping problem, and it will give us a lower bound on the optimal value of our original maximum likelihood estimation. So we will return both of those things. And if you sort of look at the results that we proved earlier, what those results guarantee is that if our relaxation is exact, then this R is going to be a globally optimal solution for our original SLAM problem. And in that case, the value that that estimate attains for our original objective is going to exactly match the optimal value of our SDP that is a lower bound on this problem. And so the equality of those two things then certifies our recovered estimates global optimality for our original post-graph optimization problem. And so the significance of this is not only do you actually get a globally optimal answer, but you can recognize and computationally certify after the fact that the thing you got is in fact globally optimal. So not only do you get an answer that's correct, but you know that you have an answer that's correct, which is really important for the safety critical applications that we want to apply these techniques to. Okay, so I know we're getting kind of close to the hour here, so I think I might quickly just give you some just to give a quick recap of what we've got so far. So thus far we've derived a convex relaxation for postgraph SLAM, and we've proved that relaxation is exact for bounded noise. And we've also developed a fast optimization technique to solve this relaxation efficiently. Last question is, okay, does this actually work in practice, right? Does this work in real life? And so just to give you an indication of what this operationally looks like, what I'm going to show you on the left is a local search technique being applied to solve one of these robotic mapping problems, starting from a bad initial configuration. And so you can see here, this technique is really kind of struggling to unfold this map estimate into something that looks reasonable, right? On the right-hand side, what I'm going to show you is a low-dimensional projection of the optimization that is being done in this higher dimensional STP relaxation, but started from that same bad configuration that was used to initialize the left-hand side. And so the punchline here basically is that because we are moving around, we're solving this problem after embedding it into this higher dimensional space where there are more degrees of freedom to move around in. Our STP relaxation-based technique is actually able to escape from the bad local minima in the area of our initial estimate, and in fact recover the actual globally optimal correct solution to this mapping problem, which more or less looks like kind of a simulated grid world in this case. So I don't know, I was pretty excited the first time I saw this. I thought this stuff is pretty cool. For those of you who maybe have, if anybody here listening has had sort of exposure to robotic mapping or high dimensional like estimation problems of this type before, seeing stuff like this is pretty neat, because ordinarily these problems are very, very hard to solve if you don't have pretty good initial estimates, as we often don't. Okay, so that's maybe a little bit of visualization. I think in the interest of time, I might skip through some of this stuff briefly. Well, no, I'll maybe cover it briefly. We did one set of experiments on simulated grid worlds where we were varying the rotational and translational noise that was being applied to our relative motion estimates, and also the size of the grid worlds that we were simulating. And so what we're measuring here basically is so we get both from this, we get an estimate that has an MLE value, what am I trying to say? What these plots are showing, they're plotting the relative suboptimality that comes from comparing the value of the estimate that we recovered with the lower bound from the STP. And we are seeing how that relative suboptimality varies as a function of angular noise, translational noise, and the size of the map in question. And the punchline here basically is that we are getting problems that are essentially, we are finding solutions that are essentially certifiably globally optimal, where the noise on the individual motion estimates is something like up to 20 degrees of angular error and over a meter of like translation error, right? Which are absolutely massive compared to what you would expect for most well-engineered robotic systems. Typical values you'd expect for this would be like, degree accuracy or less for like well-calibrated systems, and a few centimeter accuracy for like, also for, relatively well-calibrated systems. So the punchline here is, these are, in these simulations, we are finding that, this method can tolerate noise that is up to between 1 and 2 orders of magnitude larger than what you would typically expect to see while recovering certifiably globally optimal solutions to these problems. Similarly, if we look at sort of what this looks like for large-scale SLAM benchmarks, what we find, so these are real data sets, or a combination of large-scale synthetic and real data sets that are often used to benchmark the performance of large-scale SLAM algorithms. And the punchline here is that, again, we find that when we apply our technique to these examples, we again find that we get globally optimal solutions. We can solve fairly large problems. So in this case, problems that are up to, so these would be 60,000 dimensional STP problems in this case that we have to solve in order to solve this relaxation. And we can solve these problems with a time, in a matter of a few seconds, right? So instead of the thousands of seconds that we were seeing before for problems that were tiny compared to these, we can solve these problems on a scale that is operationally relevant for real-life deployment on computationally limited mobile platforms. So, so overall then, what this sort of gives us then is a certifiably correct algorithm for post-draft SLAM. It recovers globally optimal estimates for moderate noise up to about 10x the level of noise you typically expect to see in a real-life system. It can actually be made significantly faster than prior state-of-the-art techniques by exploiting the geometry of these specific Riemannian manifolds if you're very clever about how you build your optimization system. And in fact, this is actually the first practical algorithm to appear in the literature that was provably capable of recovering correct SLAM solutions under realistic operating conditions. And so in fact, this algorithm actually resolved about a 20-year-old open problem on the reliability of robotic mapping techniques, which we were pretty excited about. So if that had been it, I think we would have been pretty happy with this. But to me, the real reason that I'm excited about this work is that I view this as not being sort of the end of the story, but really as a proof of concept for a more general approach to just generating a very, very broad class of certifiable estimation techniques. So in the interest of time, I think I'm going to just quickly give you the pitch for what this looks like. But it turns out basically that if you look at what we did to actually produce our convex relaxation, the key step that we did was just recognizing that if you have a symmetric outer product like this that appears in your problem, you can simply replace this with a generic PSD matrix, and that will give you a convex relaxation. The key insight is that once you've seen this trick before, there's nothing about this that is restricted to this particular problem. In fact, this trick can be applied to any problem that is expressible as a polynomial optimization problem via a technique called moment relaxation or sum of squares relaxation. So this is a totally standard technique. I'm going to skip over the details of this, I think, in the interest of time and just wrap up. But the punchline basically is that you can apply this technique to essentially any polynomial function that you could write down. And so what this gives you then is a way of generating STP relaxations for, this gives you a methodology, sort of a recipe for stamping out certifiable estimators for any estimation problem that can be expressed as a polynomial optimization problem, which is an extremely general class of techniques. And so subsequent to our derivation of SE-Sync in particular, a bunch of people have started sort of applying these techniques to a whole slew of different problems and use this to generate similar kinds of global optimization, fast global optimization techniques for a bunch of different problems in embodied machine intelligence. So yeah, it's really kind of taken off, which is pretty fun to see. Yeah, so I think I guess I'll close with that then. So the main takeaway then, I hope that I've conveyed to you today, is that convex relaxation provides a super powerful approach for building fast global optimization methods. It enables the recovery of provably globally optimal solutions under realistic conditions, preserves the speed of existing heuristic local search-based techniques if you're clever about how you design your optimization techniques. I primarily focused on one particular algorithm just to make it concrete for the purposes of this talk. But there's tons of different extensions of this and lots of open research questions about how you can make these techniques more general, more scalable, derive stronger a priori performance guarantees, expand this into the realm of learning-based systems and so on. So lots of cool open-ended questions here to explore. And if you're interested in hearing a little bit more about this, I'd encourage you to check out our group's website. Yeah, with that, I'd be happy to take any questions you might have.
Awesome. Thanks for the talk. I'm going to react by clicking a button. I invite everyone else to do so. I'll stop the recording here.